Our final speaker of the morning is Professor Anthony Challinor. He received his PhD in 1998 for research undertaken in the astrophysics group at the Cavendish Laboratory, University of Cambridge. He was a Royal Society University Research Fellow between 2002 and 2007. And since 2017, he's been the Professor of Cosmology and Astrophysics and Deputy Director at both Keck Institute for Cosmology and the Institute of Astronomy at Cambridge. He's a core team member of Planck HFI, with particular interest in lensing of the CMB and cosmological parameter estimation. And this morning, he'll be posing the question, a distorted view of the CMB.
Thanks. Okay, thanks very much, Tony. It's a real pleasure to be here, so thanks for the invitation. So we're very, very fortunate with the microwave background that essentially we live at a time where the angular scale of the CMB fluctuations are essentially degree scale, so they're reasonably easy to measure. The amplitude is sufficient that we can also measure it. But as we've just heard in the previous talk, there are signals in other emission mechanisms that can get in the way and sort of distort our view of the microwave background. So Jacques talked primarily about galactic emission, whereas what I'm going to talk about is the distortion due to weak gravitational lensing of all the large-scale structure in the universe. So it turns out that lensing is both a hindrance in that it distorts our sort of view of the primordial universe, but it's also a blessing in that it actually tells us interesting information about the late-time universe that would otherwise be very degenerate with other features in the microwave background. So that's one of the things I want to get across in this talk, really, is that there is information in lensing that we are already exploiting. And the final part of the talk is actually going to deal with a question mark at the end of this, this title, which is this idea of whether you can get rid of the lensing effect and hence get a more pristine view of the primordial fluctuations. And we'll see that in the context of future sensitive measurements of the CMB, this is actually very important. Okay, so the basic idea is that the CMB is released at the time of recombination on this last scattering surface. The radiation then propagates through all the structure in the universe between us and the CMB last scattering surface, and it's deflected by the effect of weak gravitational lensing. So the two sort of key points here to understand are that the lenses that are relevant are quite large scale. They're typically a 100 megaparsec in size. And just because the CMB is emitted so far away from us, the sort of optimal position for lenses to lens the microwave background at a redshift of around 2, so in sort of co-moving distance, about half the way back between us and the last scattering surface. So with lensing of the microwave background, we're actually probing the universe way back here, reasonably early times in the evolution of structure, where things were actually reasonably simple. The fluctuations in large-scale structure were somewhat simpler here than they are in the highly evolved late-time universe. So the lensing deflections that are predicted are small. They're just a couple of arc-minutes in size. And because the lenses are quite large, they're coherent over degree scales on the sky. So we're expecting small arc-minute deflections that are coherently spread over a couple of degrees. Okay, so the main idea here is that in linear perturbation theory, at leading order, the deflection field is just the gradient of some potential. So this thing d is just a vector field on the sky, and that's how the photons are deflected. And that's given by the gradient of this potential phi, which is just some integral along the line of sight of the gravitational potentials, or equivalently the metric fluctuations. And if you ask what's the power spectrum of this thing like, well, it's given by this plot here. So the usual thing, large angular scales here, small here, and then this is saying the variance of this field as a function of scale. And you can see the peak at multiples L of around 60 corresponding to these degree scale coherence effects that I was talking about earlier. An important thing to note here is because we're looking at fluctuations at reasonably high redshift, as I said, the universe was kind of simpler, and you don't have to worry too much about nonlinear effects of structure formation. So in particular, the solid line here is just what you get from using the linear matter power spectrum. The dashed line is using the nonlinear matter power spectrum. And they're very, very similar. Whereas if we'd made a similar plot, if we were looking at the effect of gravitational lensing on the shape of galaxies, for example, which is a much lower redshift source, then you would see a much larger difference between the linear and nonlinear power spectra, just because you're probing the universe when it was more complex. Okay, so how does lensing actually affect the microwave background? Well, it's reasonably straightforward because lensing conserves surface brightness. So the temperature and the polarization Stokes parameters just get remapped according to these lensing deflections. So let me just show you graphically what's involved. So this is just a simulation of what the temperature, the E-mode polarization would look like in a universe without lensing. And then in the bottom panel, which at the moment is 0, are the B-modes. So I'm assuming there's no primordial gravitational waves in this universe, so there's no B-mode polarization. And then if you turn lensing on, I'll just toggle between these, you can see that you're just moving these fluctuations around. And if you look at the top panel, what's happening is that in some regions, the fluctuations are basically being coherently magnified, and in other regions, they're being demagnified. So you get this sort of anisotropic magnification across the sky according to where there are significant amounts of matter that can lens the CMB. You'll also notice that in the bottom panel now, we've generated some B-mode polarization. And this is just from the conversion of these primordial E-modes through the action of gravitational lensing. So remember, an E-mode it's a very specific sort of relation between the direction of polarization and its variation over the sky. And what lensing does, it preserves the polarization direction, but it moves those little polarization vectors around. And it can sort of destroy that very precise relationship that defines an E-mode and give rise to some B-mode polarization. Okay, so the main sort of effects in words are, because you have this magnification and demagnification over different parts of the sky, what that tends to do is smooth out the acoustic peak features in the angular power spectra of the CMB. So remember, the reason we see those acoustic peaks in the power spectrum is because there's a very well-defined length scale associated with the CMB, which is just the distance that sound can travel in the early universe from the Big Bang to the time of recombination. And that defines a coherent scale for the fluctuations. But now, if in some parts of the sky the fluctuations are magnified and in others they're demagnified, that length scale is getting stretched and contracted at different points on the sky. So you blur out that nice, precisely defined length scale. As I've said, you also generate B-modes, which will be very important for what I'll say later. And finally, you introduce non-Gaussianity. So even if the primordial fluctuations were perfectly Gaussian, by remapping them according to this lensing prescription, you generate some non-Gaussianity. And it turns out this is very, very important to actually reconstruct the effects of lensing from the CMB fluctuations themselves. So, as I said in the introduction, one thing I want to get across is this idea that although lensing distorts our view of the CMB, it does add additional information that would otherwise be very difficult to get at. So this is just illustrated in these couple of plots here. So this is the temperature angular power spectrum for two different cosmological models. The one in black is just our standard Landau-CDM model, whereas the one in red is a model where the early universe looks exactly the same, but the late time universe is very different. So this model actually has significant spatial curvature and a very low Hubble constant. And the models are just tuned so that they have the same angular diameter distance to the last scattering surface. And the effect of that is that the CMB power spectrum basically looks exactly the same. But if you look at the lensing in these models, they're very different. So the curved model with low Hubble parameter predicts a lot more lensing. So if we were able to extract this lensing information from the CMB, we'd be able to distinguish these two models. And in this way, we can do things like we can learn about the curvature of the universe or anything else that affects the late-time evolution of structure, such as dark energy, light neutrino masses, etc. But it's also true that lensing does distort our view of the primordial universe, and this is most important when we're looking for B-mode polarization. So this is just showing, again, the various angular power spectra for B-modes, this time for 3 different values of the tensor to scalar ratio. This R of 0.1 is about the current sort of upper limit, and as we've heard earlier, we don't actually know the amplitude of this, so we want to push down to much lower levels. The conversion of E-mode polarization into B-modes produces a spectrum of B-mode polarization, which on these large angular scales, these degree scales where you're interested in searching for the signal of primordial gravitational waves, essentially behaves like white noise. And you can sort of characterize that as it's almost like your instrument has an additional 5 microkelvin arc minute of noise on top of the instrument noise. So what this does is it confuses you when you're trying to search for the primordial signal. In practice, what it does, it sort of adds an additional cosmic variance to your signal, which can limit your ability to detect primordial gravitational waves in a way that I'll show later. Okay, so let me just take you through some of those lensing effects on the microwave background to say that to show you how we've detected them. So the first one of these that's important is this peak smoothing effect. So this plot here is just showing in black the unlensed microwave background, and then in red the power spectrum when you lens it. And it's clearly a subtle effect. If you look at the difference in the bottom panel, it's a few percent by multiples L of about 2,000. So it's a small effect, but it's very, very important. In fact, we have to routinely model this when we fit cosmological parameters to the CMB spectra, or else you just completely bias your inference from the CMB spectrum. And in fact, you can ask, can we actually detect this peak smoothing effect directly in, for example, the Planck data? And you can. You detect it at about the 10 sigma level. But much more interesting is to try and use this non-Gaussian imprint of lensing in the CMB to actually reconstruct the lensing effects and hence essentially make maps of what the CMB lensing deflections look like. So I don't expect you to understand all the details of this if you're seeing it cold for the first time. But the basic idea is that if you have fixed lenses on the sky and you imagine averaging over CMB fluctuations, then the lenses introduce statistical anisotropy. So you might have one region of the sky where you have some magnification, you have another region where it's demagnified, and the statistics of the CMB will look different in those two regions. And basically, by making local measurements of the statistics, you can pull out how the lenses are varying across the sky. And in practice, what we do is by using quadratic combinations of the microwave background. So we look for sort of locally anisotropic correlations between CMB fields. And that allows us to reconstruct the effect of these lenses. So just in pictures, you take the CMB, you appropriately filter it, you cross it with itself, and hopefully you pull out some map of the CMB lensing. It's very important to realize that this reconstruction is statistical in nature, so it's inherently noisy. And the origin of this noise is very much like the shape noise that you have if you're trying to do lensing with galaxies. You can just have chance Gaussian fluctuations in the microwave background that mimic the local effects of gravitational lensing. So this is just a simulation at the sort of level of sensitivity of the Planck satellite. This is the input lensing field, and this is what you recover at Planck noise levels. So these are clearly correlated, but this is much noisier. You can quantify that noise by looking at a power spectrum of the noise. So this is the signal we're after, the lensing signal. And then for different quadratic combinations of the data, combining temperature and polarization, you get these different noise curves. The Planck measurements are such that you're completely dominated by the temperature information. So that's this TT quadratic estimator, which has noise given by this red curve. So what you can see is it's larger than the signal you're trying to measure everywhere, so your maps are inherently going to be very noisy. You can do a little bit better by including polarization information, and in particular this TE combination. And if you fold all of these together, you get this minimum variance combination, where you're just getting a signal to noise of 1 on a handful of modes at L of about 60. So that's where we are with Planck. As I'll show you at the end of this talk, with much better polarization data, we can push this much further, and we can get noise levels that are way down here that allow you to make signal-dominated lensing maps over a much broader range of scales. Okay, so if we do this with the Planck data, this is the reconstruction that you get. You can also do this with ground-based measurements. The ground has the advantage, of course, that you can have much better angular resolution. And angular resolution is actually important. Imagine you're trying to reconstruct small-scale lenses on the sky. Then what you want is lots of small CMB fluctuations in front of those lenses, which are all coherently affected by the lens. And if you're going to image those small-scale fluctuations, you better have good resolution. So this is just an example of a map from the South Pole Telescope, and this from the Atacama Cosmology Telescope. And the signal to noise in these maps is much higher than the lensing map from Planck. However, these only cover a small part of the sky. This is 2,500 square degrees. This is just 500. So statistically, the Planck map is actually much more powerful at the moment. Once you've gone and made this map of the lensing deflections, you've essentially got another cosmological observable that you can do statistics with. So the first thing you can do is take its power spectrum. So this plot is just showing a compilation of both Planck and those ground-based measurements, what you get if you form the power spectrum of the lens reconstruction maps, compared to the black solid line, which is not a fit to any of this data, but it's just the prediction in the Landis CDM model for what you would expect the lensing of the CMB to look like. And what you can see is there's really beautiful agreement. I think this is a really fabulous test of this model. We calibrate the model with just these 6 parameters based on observing the universe at redshift of 1,000. And then we make a prediction for what we ought to see the lensing deflections to look like at lower redshift. And it's beautifully consistent.
You showed that plot with minimum variance estimator. It was touching the spectrum to be measured at about 40 nL or something.
Yeah, that's right. Yeah.
But when you look at Planck, kind of pink or whatever that color is, brown,
Yep.
boxes, they just start losing it exactly there. And they're tighter in estimator vertical direction, going to higher L.
Well, you have to remember, so those noise curves I was showing, that's essentially noise per mode, right? So your power spectrum, you've got lots of modes. For a given delta L, you've got many more modes at high L than you have at low L. So that's why you're winning out. Yeah.
So why are horizontal widths the same on the boxes?
They were just chosen to be. I mean, you have complete choice over how you bin your spectral measurements. Okay, so you can actually do something useful with these measurements. So this is just an example. So this is trying to constrain models beyond the Landis CDM model. So remember I showed you a plot earlier of 2 models that were very degenerate in the temperature power spectrum. So this curved model and the standard flat Landis CDM model. And the fact that those 2 models look very similar and both fit the temperature data well gives you this very significant degeneracy direction if you plot things in the omega matter, omega lambda plane. So flat universes would lie along this dashed line, and then this so-called geometric degeneracy gives this large sort of degeneracy along this direction. So these models down here are those curved models with low Hubble parameter. If you add in the lensing information, these models significantly overpredict the amount of lensing. So they correspond to this cloud of points up here that have large lensing deflections, and they're completely ruled out by the Planck lensing data. So if you put the lensing in, you narrow down to this little region here, or equivalently up here, which is very consistent with a flat universe. So by making use of the lensing information, just from the CMB alone, we can constrain curvature at the sub% level. And in fact, you can do significantly better if you also fold in things like baryonic acoustic oscillations from galaxy clustering. One of the other very nice things we can do is cross-correlate these lensing maps with other traces of large-scale structure. And this is a field that's really sort of just beginning, but in the future, I think there's tremendous scope for doing interesting things here. So this is an example from a paper correlating a lensing reconstruction from the South Pole telescope with galaxy clustering data from the science verification data from the Dark Energy Survey. And the sort of motivation for doing this is that you can actually sort of look at the evolution of structure over cosmic time. So if you just look at CMB lensing, that's just an integrated measure. It doesn't have any information about different redshifts. Whereas, of course, galaxy surveys, if you can get photometric redshifts or spectroscopic redshifts for the galaxies, you can actually see how things, how they're structured over time. But the problem is that galaxy clustering is a complicated business. Galaxy formation is inherently difficult, and it's a biased tracer of large-scale structure. But if you combine lensing and clustering, you can break the degeneracy between how biased galaxies are relative to the dark matter and how clustered the dark matter itself is. So just symbolically, if you measure galaxy clustering, so that's represented by this observable sigma, that's proportional to the amplitude of structure squared and the bias squared, whereas if you cross-correlate lensing and galaxy clustering, you only have one factor of bias. So you can try and basically pull these two things out as a function of redshift, and hence chart both the evolution of bias and cosmic structure with redshift. So going forward, this will be an extremely powerful probe of how structure is evolving, and hence whether our ideas about dark energy as the agent for the acceleration of the universe are correct. Okay, so the final part of the talk, I want to address that question mark in the title, which was about whether we can sort of undo the effects of gravitational lensing. So to motivate this, let me just show you current direct measurements of the B-mode power spectrum. So these are all ground-based measurements from BICEP Keck, ACPOL, SPT Pol, and Polar Bear, compared to the spectrum that we expect for the lens-induced B-modes, which, remember, are coming from conversion of E-mode polarization into B-modes. And there's large error bars on these points, but they're nicely consistent with the prediction. Of course, what we're really interested in is what's happening over here on these degree scales, where there might also be the additional signature of primordial gravitational waves. So this is the plot I showed you earlier, remember, with our lensing B-modes and different amplitudes of the tensor to scalar ratio. And basically, if you're trying to constrain models with a tensor to scalar ratio below about 10 to the minus 2, you become troubled by these lensing B-modes. And you have a choice. You either live with them and suffer the additional variance, or you try and do something about it. So the way you can do something about it is basically as follows. So imagine we do one of these, say, lensing reconstructions using the non-Gaussianity in the CMB to estimate the lensing potential phi. We also go out and measure the polarization, so we have some estimate for what the E-mode polarization is like. Well, the B-modes on the sky from lensing come from basically converting the E-modes by this lensing potential phi. So you can just write down an estimator for what those B-modes are and subtract it off from what you measure. And hopefully, the result, which is these resulting delensed B-modes, has less contamination than what you started with. How well this is going to work will really depend on how correlated your estimate for the lensing potential is with the true lensing signal on the sky. So if you can make this correlation that I'll call rho L, if you can make it very close to 1, you will significantly suppress the lensing effects in these delensed B-modes, and hence your power in your delensed B-modes will be significantly lower than it was before you started. So you'll push this blue line down to somewhere lower in the plot. Okay, so the reason this is important, of course, is because we want to test ideas about the early universe. And how important lensing is actually depends on many things. It depends on the noise level in your experiment. If your noise is significantly large compared to that 5 microkelvin arc minute additional noise that lensing is generating, then lensing isn't really an issue anyway. You're just limited by instrument noise. But we're actually already at a stage where experiments, their pure instrument sensitivity is actually better than 5 microkelvin arc minute. So lensing is already becoming important. It also actually depends on the size of the signal. So if you're, if nature were very kind to us and the amplitude of the gravitational waves was high enough, then lensing wouldn't be troubling anyway, because the signal would just be way up above the lensing signal. We don't actually know if that's the case yet. Current upper limits on B-mode polarization are of about 0.1, which is well above the lensing signal. But we want to push much further down than that. So what this plot is just showing is for sort of different models characterized by different tensor-to-scalar ratios, what the 3 sigma error on the tensor-to-scalar ratio would be for a core-like experiment with a couple of microkelvin arc minute instrument noise levels. And in each case, the solid bar is just showing what the error on the tensor-to-scalar ratio is if you didn't do anything about lensing, whereas the dashed line is showing what you would get if you could completely remove the lensing signal. So what you find is that if your model has a very low tensor-to-scalar ratio, lensing is important on all scales, and it degrades things by about a factor of 6. Whereas for models with large values of R, then lensing is less important. And of the 2 sort of possible scales where you can try and constrain gravitational lensing, you can either use the reionization signal, so that's a sort of large angular scale signal, or the recombination signal, which is on smaller angular scales. Lensing is sort of more troubling for the recombination signal than the reionization signal, because this signal has a kind of big bump on large scales that pokes up above the lensing signal. Okay, so for example, if you want to do things like test Higgs inflation or equivalent sort of Starobinsky model, lensing becomes rather critical if you're trying to test these models at high significance. Now, it's very important to realize that even though we're trying to constrain degree scale B-modes, it's actually lenses on reasonably small scales that are important. So this is just showing at a multipole L of 60 what scale or what multipole of lenses are important. And there's a broad range of scales going all the way up to L of about 1,000 that contribute significantly to the B-mode power at L of 60. So what you want to do is try and remove the effect of lenses over a broad range of scales. And if you're going to do that by using a reconstruction of lensing from the microwave background itself, currently that's very challenging. The reason is just because, as I said, the reconstruction is noisy, and in particular on the relevant scales for B-mode polarization, which are these scales here, the reconstruction is just too noisy, and your template is just not very well correlated with the true lensing effect on the sky. So this plot is just showing, as a function of angular scale, what this sort of efficiency or the correlation coefficient squared is between your lensing reconstruction and the true lensing signal. So the efficiency is reasonably good on large angular scales, but it's poor on the scales that you would want to delens the B-modes. So this suggests we look for alternatives to, at the moment, for alternative ways of delensing the microwave background. And I'll just mention one, which is to use the cosmic infrared background. So we heard a little bit about this earlier. This is the integrated emission from infrared emission from star-forming galaxies. And because it's an integrated signal, it stretches out to high redshift. And it turns out to be very correlated with the CMB itself. So it's correlated at about the 80% level. So potentially, this is a very good sort of proxy for the lensing signal in our universe, which we can use to try and delens the microwave background. So I'm getting short of time, but let me just show you that this at least works. At the moment, our polarization measurements are kind of noisy, so there isn't much advantage to actually trying to delens the B-modes themselves with things like the cosmic infrared background. But we can try and do a similar thing with the temperature fluctuations. So this is just an example where we took the Planck temperature map and we basically just ran it backwards using the cosmic infrared background as an estimate for what the lensing deflections would be. And then we took the power spectrum of that map and compared it to what we started with. And if you have delensed this map, what you would hope to see is a sharpening of the acoustic peak features. Amazingly, it actually works. So you see this oscillatory pattern in the difference of the two spectra. Here, for example, there's a prominent acoustic peak, which gets lowered by lensing. You delens it, and it goes back up again. This demonstrates that you really can delens the microwave background with the cosmic infrared background. And in fact, more recently, we've actually been able to delens B-modes. In this case, this is from the South Pole Telescope team using the cosmic infrared background, whereas this is from some work that I did with colleagues in Sussex using the Planck data and actually delensing B-modes with an internal lensing reconstruction from the CMB itself. So these are very much proof of concept. You don't actually gain anything in terms of our inference about inflationary cosmology because the data is just too noisy, but it's a proof of concept. It shows you can do it in principle. Okay, so finally, let me just say that the future is very bright for this field. Essentially, if we're going to make these very precise measurements of polarization, we get this lensing signal for free. With Planck data, we're currently at these sort of noise levels. So this is showing the temperature-based reconstruction, or the sort of optimal thing combining all the data. This is the signal. Whereas with something like a future space mission, where you've maybe got CMB sensitivity of a couple of microkelvin per arc-minute pixel, we can really push these noise levels down on these reconstructions. And in particular, this particular channel where we combine E-modes and B-modes is very promising for getting signal-dominated measurements all the way out to multiples L of several hundred, or actually, if we could improve the resolution, all the way to L of about 1,000. So you can get hundreds of thousands of resolved modes with which you can learn something about the late-time universe, and you get it all for free by making these precise measurements of the CMB lensing signals. Okay, thank you very much.